7.3, the last section of new material before your test. On the inside back cover of your textbook, there's a collection of about 30 integration formulas. And I have copies, just in case you don't bring your book to class, or you want to have this in your back pocket at all times because you never know when you're going to want to integrate something. You can laminate it, fit in your wallet. Yeah. You cannot. You can write any of these you want on your paper, but I will provide you with anything that you need from here on the test. You don't get to bring this table with you to the test. But I will, like at the front top of your test, I might give you 3 integration formulas from there, and there might be one problem where you have to pick one of those and apply it. Okay, so these formulas are general. They allow us to quickly calculate some complex integrals without reinventing the wheel. So some of these formulas were derived using integration by parts or U substitution, which means that when you're applying one of those formulas, you could also solve it by integration by parts or U substitution. Most of the formulas, though, on here involve techniques we haven't seen yet, but we can still use this table fluently. It's kind of like a low-tech version of Mathematica, right? So you don't really understand where the formulas come from, but that doesn't mean you can't use them, right? So many of these are derived by parts or U substitution. In fact, I think number 8 in your was in your homework to derive this formula. So these would also make excellent bonus questions asking you to prove one of these formulas for the test. All right, so when you use the table, you look at the integral that you're given, and you try to find something in the table that matches its form exactly. Has to match the form exactly. So we'll just dive right in. We have x to the 5th times the ln of x. Is there a formula in this table that has the form of x to the 5th times ln x? Which one? Number 13. It says x to the n times the ln of x. So let's just write down what that formula says. It says that the integral of x to the something times the ln of x dx is equal to 1 over n plus 1 times x to the n plus 1 times the ln of x minus 1 over n plus 1 squared x to the n plus 1 plus c. And then there's a couple notes over here. It says you can't use this formula if n is -1 and x has to be positive. What is n in our problem? 5. Yeah, so this is x. My problem has x to the 5th, and you can use this for x to the anything. So in our case, x is 5. So if I want to do the integral of x to the 5th, ln x dx, I just have to replace all my n's in the formula with 5s, and I'm done. So this is going to be 1/6, because 5 plus 1 is 6, right? X to the 6th times the ln of x minus 1 over n plus 1 is 6 squared is 36. X to the 6th plus c. Oops. Done. Is this your favorite integration technique? No? What's your favorite? By parts. You could also do this by parts, yeah. All right, we have 1 over cosine cubed x dx. Is there any formula in this table that has the form, same form as 1 over cosine cubed? 21 is 1 over cosine to the m of x. All right, why can't I apply 18 here and just write that as cosine x to the -3? Why can't I apply number 18? Yeah, because you have to look to the end, and there are the restrictions are listed there, and it says n has to be positive. So I'm going to use number 21. So I'm just going to write the formula down. And it says that the integral of 1 over cosine of x to the m dx is 1 over m minus 1 times sine x over cosine to the m minus 1 of x plus m minus 2 over m minus 1 times the integral of 1 over cosine to the m minus 2x dx. So my formula for the integral has an integral in it. So fingers crossed that that new integral will be easier than the original. So what is m in this case? 3. So this is the integral of 1 over cosine, replacing that m with a 3. So then I just replace all my m's in the answer with a 3. So I get 1/2 sine x over cosine squared x, because m minus 1 would be 2, plus m minus 2 is 1, m minus 1 is 2, 1/2 the integral of 1 over cosine x dx. So now I have to take the integral of 1 over cosine x, and I'll be done. Do we know that off the top of our heads? Yeah, we don't, but it's in the table, number 22. So I can just write it down. So I end up with 1/2 sine x over cosine squared x plus 1/2 times the antiderivative of 1 over cosine x from the table is the ln of the absolute value of sine x plus 1 over sine of x minus 1 plus c. Oh yeah, because I have my 1/2 from my formula, and then I have my 1/2 from this formula, so this is a 4th. Thank you. So I do apply 2 formulas from the table to get this one. The first one was 21. And then I used 22 later on. That's fine. That's fine. I mean, with trig stuff, you can simplify all day, right? Just keep using trig substitutions and no, just leave it. Okay, so let's look at C. I've got sine to the 4th times cosine cubed. Anything in this table have that form? Well, 17 and 18 are just plain old sine and plain old cosine. 23, yeah. Somebody said 15. Oh, yeah, 15 you could use. P of x would have to be, oh no, you can't use it. Sorry, because it's sine of ax, not sine to something. Yeah. So, but 23 is sine m cosine n. And then there's several sentences about how to handle this, right? So it's broken into several cases. It says if m is odd, let w be cosine x. So your book uses w's instead of u's in the u substitution. I don't know if you noticed that, but so they're telling you to use a u substitution where u is cosine x. But that's only if m is odd. What is Rm? It's even. It's a 4, right? m is 4, and n is 3. So it says if n is odd, so that's the one that we're doing, m is odd, then we're going to let w be sine of x. I'm going to call it u, because that's what we did in class. Okay. And do a u substitution. Okay. And then there's more cases. So if that wasn't true, right, if n wasn't odd, you would just keep reading until you found the case that was appropriate. All right, so du dx is cosine x, which means dx is du over cosine x. We go to our integral, sine to the 4th, cosine cubed, and do my u substitution. So this is going to be the integral of u to the 4th times cosine cubed x times dx, which is du over cosine x. So now we simplify and cancel, and my goal is to have only u's remain, right? So I can cancel the cosine x in the denominator with one of my cosine x's from the numerator. And now I have u to the 4th times cosine squared x du. Yeah, I'm going to use a trig substitution, a Pythagorean identity. So cosine squared, if I could rewrite that in terms of sine, then I can use my u's to replace it. So just to remind you, right, the Pythagorean identity, if there's only one trig identity that you ever remember, it should be this one. So I can solve this for cosine squared, and I get 1 minus sine squared. So then I can go back to my integral and replace my cosine squared with a 1 minus sine squared. Okay, and then the whole point of that substitution is that now that I have that written as sine squared instead of a cosine squared, I can replace the sine with a u. And then I'll distribute. This is the integral of u to the 4th minus u to the 6th du. And then the antiderivative is easy, right? Just use the power rule. So increase the exponent by 1 and divide by the exponent. And should I just circle it? Am I done? What do I have to do still? I got to put the u back in. Substitute back. So I get sine to the 5th minus sine to the 7th over 7 plus c. So in that one, the table didn't so much tell us what the answer is, but what technique we should use to find it. Okay, sometimes you need to do a u substitution first before you can apply the integral. So we're looking at this integral. We have e to the root x times the sine of 2 root x over root x. And I want to find the antiderivative. So I say that's complicated looking. I'm going to try my table. Is there anything in the table that looks like that or close to that? It's got to have e to the something, and it's got to have the sine of something. 8, yeah. 8 looks kind of like that. But does it look exactly like that? No. And it has to look exactly like that to apply it. Right? So what I'm going to do is I'm going to try to make a substitution. So 8 says e to the ax times the sine of bx. So if these were plain x's instead of root x's, then it would look closer. I'd still have this weird denominator thing, but Let's just see what happens if I try to make them plain x's. So I'm going to let u be the square root of x, which means du dx is 1/2 x to the negative 1/2, which means dx, so I multiply both sides by dx, and I'm going to multiply both sides by 2. So I'm going to have 2 du, and then divide both sides by x to the negative 1/2, or multiply both sides by x to the positive 1/2. 2x to the 1/2 du. And if your algebra doesn't come out looking, if you did your algebra a little bit differently so that you ended up with 2 over x to the negative 1/2 du, it's fine. Right? We're just going to end up doing some simplifying, and I was just looking ahead a little bit. That's why I wrote it like that. All right, so I have my original integral, e to the square root of x times the sine of 2 square root x over square root x dx. And then I'm going to make my substitutions. So this becomes the integral of e to the u times the sine of 2u over the square root of x times dx, which is 2 square roots of x. Yep. But it's going to cancel anyway. I could write these as u's or square root x's. Either way, they're going to cancel with each other, right? So this is the integral of e to the u sine 2u du. And now it looks exactly like number 8. Oh, I have a 2 from that 2 there. Pull it out of the integral. So now that it looks exactly like number 8, I can just apply the formula. So in number 8, we have e to the ax sine to the bx. So what is a in my problem? 1. And what is b? 2. A is the coefficient on the exponent with the e, and b is the coefficient on the input of sine. So then I just go plug these in, and it says I have 1 over a squared plus b squared. So 1 squared plus 2 squared is 5. Oh, I still need the 2. One-fifth e to the ax, or au, because my variable is u now, times a sine bx, so sine 2u minus b cosine bu, 2 cosine 2u plus c. Yeah, thank you. I am not done. I got to plug in my u's, which are square root x's. So see if I can carefully erase here. So this was a u. This is the sine of 2u, and this is cosine 2u. There we go. Now I'm officially done. That 2 in the very front came from this 2, which was in front of the whole integral, which came from this 2 that popped in when I did the u substitution, because dx was 2 times the square root of x. Just that. Any other questions? Where stuff came from? So using the table is often just an exercise in very carefully copying down the formula and plugging in the right stuff. Yes, Sephora. When you're doing U substitution, often there'll be a constant left in front of the du, and you pull that out in front of the integral. If it's in the numerator, it just is plain old 2. If that 2 were left in the denominator, you would pull out a 1/2. I say that just because it's a common mistake. There'll be a 2 left in the denominator, and people pull it out and make it a 2 instead of a 1/2. Yeah. We have fractions. Okay. So here are 3 similar looking integrals. They all have a quadratic denominator. And they're going to have 3 very different solution methods. So let's look at the first one, 1 over x squared minus 8x plus 15. Is there anything in my table that has that form, or could be made to look like something in the table? 26. It's 1 over, and it's a factor, 2 factors, x minus a, x minus b. So if I could factor this, I can make it look like something from the table. And it does factor to x minus 5, x minus 3. So number 26 says that the integral of 1 over x minus a times x minus b dx equals 1 over a minus b times the ln of x minus a minus the ln of x minus b plus c. So in my case, what is a and b? Five and 3. Yeah, because it's already of the form x minus, so the thing after it is the a and the b. So in my case, a equals 5 and b equals 3. You can do multiplication in either order, so I could have written this x minus 3, x minus 5. Your a's and b's would be reversed. The answers will be equivalent. So if I plug in 5 and 3 here, I get 1 over 5 minus 3 is 2. So I have 1/2 times the ln of x minus 5 minus the ln of x minus 3 plus c. Yes, you could do that with partial fractions. That partial, which we have not yet learned, but that is the technique that you would use to actually derive this formula. It came from partial fractions, which is a technique we're going to learn after the first test. So that one's pretty straightforward, right? Just look in the table, plug in a and b, and you're done. All right, let's look at part B here. All right, x squared over x squared minus 8x plus 15. Is there anything in the table that looks like that? 26, but it's not quite, because in 26, the numerator has to be 1. What would you do? So there's nothing in the table that looks exactly like it, right? Do you guys remember polynomial long division from like college algebra or maybe pre-calc? Vaguely. If you kind of remember it, that's good enough. I'll just remind you how to do it. you could, if you move that x squared to the denominator, so it becomes x to the negative 2, and distribute it, right? You could, but then that thing that results isn't any easier. Yeah. There'd be nothing in the table that matches that. So I might post both lecture videos because in the last class I spent 20-25 minutes trying random stuff for this problem. I did exactly what you just suggested. I moved the x squared down to the denominator. I tried a U substitution. I tried partial fractions, which is something that you guys don't even know how to do yet because I just had no idea. Well, I had lots of ideas. None of them worked, right? So what ends up working is the fact that the numerator and the denominator have the same exponent. If the numerator is bigger or equal to the denominator in terms of degree, you can divide it. You can divide the two. So a fraction bar is like a big division sign, right? So let's see what we get when we divide x squared by x squared minus 8x plus 15. So x squared divided by x squared minus 8x plus 15. So remember when you're doing long division, if there are terms missing, you just put in zeros. Yeah. All right, so then it's just like division of regular numbers. So let's just say I wanted to do 30 divided by 7. How many times does 7 go into 30? 4 times. 4 times 7 is 28. My remainder is 2. How do I know that I'm done? Because 7 doesn't go into 2, right? Okay, so what do I do with that remainder? 2/7. Okay, so I'm going to try to mimic this procedure, but with polynomials. So each term of a polynomial is like place value in the real numbers. All right, so when I did this 7 goes into 30, really what I was asking myself is what do I multiply 7 by to make 30, right? So I'm going to look at just my leading terms here, and I say, what do you multiply x squared by to make x squared? 1. So that's just a constant, so I put it over the constant term. Right, like when I did 7 times what gives me 30, I said 4, and I put it over the ones place, because it was just a plain old 4. Okay, so now I do 1 times my whole thing here, just like I did 4 times the 7. I do my 1 times my divisor, and I get x squared minus 8x plus 15. And then here I subtracted, right? 30 minus 28. Here I'm going to subtract these. I'm going to subtract the whole thing, which means distribute the negative. X squared minus x squared is 0. 0 minus negative 8 is 8. And 0 minus 15 is negative 15. All right. Am I done? Yeah, right. But does x squared minus 8x plus 15, can that go into this any further? No, because the degree of the x squared is bigger than the degree of the 8x term. So I just move that up and I would say plus, because really 4 and 2/7 means 4 plus 2/7, right? So I move this up and I have 8x minus 15 over x squared minus 8x plus 15. All right, so this is equal to the original fraction, right? So I would say x squared divided by x squared minus 8x plus 15 equals 1 plus 8x minus 15 over x squared minus 8x plus 15. All right, so if I wanted to take the integral of this guy, that would equal the integral of this guy. Good? All right, so the whole point of doing that, the reason I did it, is that now this is the integral of a sum, right? 1 plus this fraction. And when you take the integral of a sum, you can do each integral separately. So this is the integral of 1 dx plus the integral of 8x minus 15 over x squared minus 8x plus 15 dx. All right, what's the integral of 1 dx? X. Antiderivative of 1 is x. And then I look at this new thing that I've got here, which does look hideous, but 27 from the table is something linear over a factorable quadratic, right? And that's what we have here. So in this case, this is cx plus d, so c is 8 and d is negative 15. And then my denominator, when I factor it, a is 5 and b is 3. So I would say this integral looks like number 27, a is 5, b is 3, c is 8, d is negative 15. And then just copy down the answer, plugging in all those numbers. So I still have my x. And then no reason to do that. Okay. So I have 1 over a minus b. A minus b is 2. Right, right. Because it's always, it says x minus a. So the minus sign is part of the formula. So a is just what comes after the subtraction sign. And if this were a plus 5, your a would be negative 5. All right, so that's 1/2 times AC plus D. Okay, so A times C is 40 plus D is 25 times the ln of x minus A minus BC plus D. So B times C is 24 plus negative 15 is 9 times the ln of x minus b plus c. Ta-da! So the key there to being able to apply formulas from the table was the division. Right? The degree of the numerator and the degree of the denominator were the same. Anytime the degree of the numerator is the same or bigger, do a division, and that will leave you with something easy to integrate plus something you can use the table to integrate. You cannot, but I will give you any formulas that you need from here. So I'll write the question and then I'll say, okay, they could do this problem with, say, number 19, and I would give you like 17, 18, and 19, right? Like I'll give you 3 and say, which one do you use, and then use it. Okay, so all right, next one. 1 over x squared minus 8x plus 18. So this is almost like A, except what? Yeah, it doesn't factor. I could use a quadratic formula, and maybe it will factor, and it's just ugly, right? It might be like x minus root 3, x plus root 3, or something like that. But let's check. How do I check to see if something factors? What's that? Oh, that's what we're going to do next. But first, we got to see if it factors. B squared minus 4ac, the thing under the radical in the quadratic formula. If it's positive, it factors. Ugly maybe, but it'll factor. If it's negative, that means that this thing has no x-intercepts and therefore no real zeros, and therefore doesn't factor. Be an irreducible quadratic. Because we don't ever deal with complex numbers in this class. So if there were i's, if you have to use i's to make this factor, you just say it doesn't factor. So b squared, so that would be negative 8 squared, minus 4 times a times c. Gives me a negative number. So that means if I were to apply the quadratic formula, the number under the radical would be negative, so this thing does not factor. So I can't apply, what was it, number 26? I can't apply number 26 because I can't factor my denominator. We call that an irreducible quadratic. So instead, I'm going to complete the square on that denominator. So I'm going to basically do a fancy manipulation to make it look like something in the table. And that fancy manipulation is called completing the square. So this is going to be the integral of 1 over x squared minus 8x. And then completing the square basically means adding something and subtracting that same something. Right? So this is what makes it a fancy manipulation, is that I'm adding and subtracting the same amount, which means I'm not really changing this thing at all. I'm just going to change its form. So the thing I add, right? The thing I add, I'm going to choose strategically so that that trinomial, x squared minus 8x plus something, factors to a perfect square. Right? It's going to factor to a perfect square binomial. So my goal is to choose that thing so that I end up with something squared. So that what is in that, under that blue curly bracket, has to factor to something squared. Which, so yeah, if you choose that thing to be a 16, x squared minus 8x plus 16, how does that factor? Close. X minus 4 squared. Yeah. And the shortcut for choosing that number is to take half of b and square it. So take the negative 8, take half of it is negative 4, square it as positive 16. All right, but then I added 16, which changes the denominator. So to keep the denominator the same, I have to also subtract 16. And then this part in the blue curly brackets factors. And then what's left is negative 16 plus 18, which is plus 2. All right, is there anything in my table that looks like that? Or close to it? Yeah, 24 from your table looks something like this, except in the table, this is, instead of x minus 4 squared, it's just a plain old x squared, right? We've got 1 over, if this just said x squared plus 2, that would work, right? My a would be a root 2, because this is x squared plus a squared. 24. Oh, 26 will not work because the denominator, that's not written as the factor of two things, it's the sum of two things. And it has to look exact. Okay. So if you use 24, I have to do another manipulation to make this work. U substitution, yeah. Let u equal x plus 4. Then du dx is just 1. Thank you. Minus 4. Du dx is 1, which means du equals dx. Right? So there's my u substitution. Plug it in and I get the integral of 1 over u squared plus 2, and then dx is equal to du. And now it looks exactly like the thing from the table. 24. 24. So almost like number 24. So this integral looks almost like number 24, a quick u substitution, and it looks exactly like number 24. a would have to be the square root of 2. Right? Because when you square root 2, you get 2. So a is square root 2. So then I just plug in using this formula, and I get 1 over a, 1 over root 2, times the arctan of x over a, but x is really u, right? So this would be u over root 2 plus c. And then the last thing I have to do is substitute back, replace my u with x minus 4. Yeah. So those last two are tricky uses of the table where you have to do a significant algebraic manipulation before you can use the table. Oh, I don't care about square roots in the denominator. That's fine. Nope. Okay, so as you can see, if you can factor a polynomial in the denominator, do it, right? If the degree of the numerator is bigger than or equal to the degree of the denominator, try long division. If the denominator is an irreducible quadratic, meaning you can't factor it, try completing the square. You will not have your book's table of integrals in front of you for the test. I will provide any complicated formulas that you'll need. All right, so now you can do some practice using the table like real engineers did it. Yeah.